Welcome. Today we will build a complete understanding of Mel spectrograms, from raw sound waves to the exact feature used by modern speech AI. We will cover 6 ideas in sequence. What sound is, how we digitize it, how we find its frequencies, why we warp them to the Mel scale, how we build the filter bank, and why we compress with a logarithm. Sound is air pressure varying over time. When something vibrates, a vocal cord, a speaker cone, it pushes and pulls the air around it, creating a pressure wave. The height of the wave is called its amplitude. A larger amplitude means a louder sound. A microphone measures air pressure thousands of times per second. This is called sampling. Speech recognition systems typically sample 16,000 times per second. Each sample is stored as a number between -1 and +1. The result is a long sequence of numbers. A one-dimensional array representing the audio waveform. Here is our raw audio waveform. The problem is that the frequencies change constantly as we speak. We cannot analyze the entire signal at once. The solution is to slice the waveform into short, overlapping frames. Each frame is 25 milliseconds long. We step forward 10 milliseconds at a time, so adjacent frames share most of their content. But simply cutting out a chunk of audio creates sharp edges in the frequency domain. Those sharp edges smear energy everywhere, a problem called spectral leakage. The Hamming window tapers smoothly to 0 at both edges. Multiply the audio frame by this shape and the sharp edges disappear. No more spectral leakage. This is the standard first step in speech processing. The fast Fourier transform, or FFT, takes one windowed audio frame and decomposes it into its constituent frequencies, its power spectrum. This is the power spectrum of one audio frame. The horizontal axis shows frequency, from 0 to 8,000 Hz. The height at each frequency tells us how much energy is there. Peaks in the spectrum reveal the resonant frequencies of the vocal tract. These are called formants, and they are what distinguishes one vowel from another. But there is a problem. The spectrum is on a linear scale. It allocates just as many frequency bins above 4 kHz as below. For speech, the important details are all at low frequencies. We are wasting most of our representation on frequencies that barely matter. Human pitch perception is not linear. The difference between 200 and 400 Hz sounds enormous to us. That is a whole octave. But the difference between 5,000 and 5,200 Hz is barely audible. Our ears care far more about low frequencies. To match human perception, we use the Mel scale, introduced in 1937. It uses a logarithm to compress high frequencies. 1000 Hz maps to exactly 1000 Mels. That is the reference point. Here is the comparison. The gray diagonal is a pure linear scale. Each frequency gets equal space. The orange Mel curve bends. Below 1 kHz it is nearly linear. Above 1 kHz it flattens, compressing the high frequencies just as the human cochlea does. Now we apply the Mel filter bank. We construct a set of triangular filters, typically 80, spaced evenly on the Mel scale and projected back into linear hertz. At low frequencies, the triangular filters are narrow and tightly packed, giving us fine detail where we need it. At high frequencies, the filters grow wider, because our ears cannot distinguish small pitch differences there anyway. Each triangular filter is multiplied with the power spectrum. The result is a single number, the total energy inside that filter's frequency band. 80 filters produce 80 numbers, 1 per Mel band. After filtering, each audio frame becomes a column of 80 numbers, 1 energy value per Mel band. Now stack hundreds of those columns side by side, one for each successive audio frame, and you have a two-dimensional heat map. This is the Mel spectrogram. Time runs along the horizontal axis. Mel frequency runs vertically. Bright cells mean high energy. Dark cells mean silence. This two-dimensional image is the Mel spectrogram. There is one more problem. A loud vowel can be a billion times more powerful than a quiet consonant. If we feed those raw numbers to a neural network, the loud sounds dominate and the quiet sounds are invisible. The solution is to take the logarithm. We convert the energy values to decibels using this formula. We add a tiny epsilon to avoid taking the log of 0. Look at the difference. Before the logarithm, The loud sound towers over the quiet one. After the logarithm, both fit in a manageable range. The quiet sound is still visible. The network can learn from it. Let us walk through the full pipeline one more time. Start with the raw waveform. Slice into overlapping frames and apply a Hamming window. Run the FFT to get the power spectrum. Apply the Mel filterbank to compress into 80 bands. Take the log to get decibel values. The result is the log Mel spectrogram. The log Mel spectrogram is the final output, a compact two-dimensional image that represents the audio. This is what we feed directly into a neural network. Because the Mel spectrogram is a two-dimensional image, a convolutional neural network can process it directly. The CNN slides a small kernel across the image, detecting local spectral textures, like formant transitions and harmonic stacks. There are three key reasons models perform so well on Mel spectrograms. First, the representation is perceptually aligned. It matches how we hear. Second, it is compact, 80 Mel bands instead of 512 FFT bins. Third, the spatial structure is preserved. Neighboring cells are neighboring frequencies, so convolutional filters find meaningful local patterns. MFCCs, Mel frequency cepstral coefficients. A simply a log Mel spectrogram with one extra step, a discrete cosine transform, or DCT. The DCT mathematically removes correlations between the Mel bands. In the 1990s, speech models used Gaussian mixture models, GMMs, which needed uncorrelated inputs to function correctly, so MFCCs were the standard. The comparison is clear. The log Mel spectrogram preserves spatial order, is directly usable by CNNs, and is the standard for modern deep learning. MFCCs destroyed the spatial structure with the DCT. That is why they fell out of favor once neural networks took over. Let us recap all 6 steps. Sound is digitized at 16 kHz. We slice it into 25 millisecond overlapping frames. The FFT gives us the power spectrum for each frame. The Mel filterbank compresses it to 80 perceptual bands. We take the logarithm to compress the dynamic range. Stacking all frames gives us the two-dimensional log Mel spectrogram, the feature that modern speech models use as their input. Here is a final log Mel spectrogram. Every spoken sound leaves a unique fingerprint. Bright regions for loud-voiced sounds, dark regions for silence. Modern speech recognizers, text-to-speech systems, and audio classifiers all start here. You now understand exactly what a Mel spectrogram is, why every step exists, and why neural networks love this representation. If this was helpful, please like and subscribe. It really helps this channel. See you in the next one.